Good morning, good afternoon, everyone. Before we begin, can I see by a show of hands if you can hear me in the questions? I guess there is attendees pane that you can raise a hand. Thank you very much, ladies and gentlemen. Thank you. Thank you all. So we are all to go. I know that you can see my slides. So let's move on. On behalf of Web-Based Solutions, I would like to welcome you to today's webinar, Data Science for Architects. My name is Mikhail Vladimirov. I'm with Web-Based Solutions. Some of the courses related to the topics discussed in today's webinar will be given to you at the end of the presentation. We've got quite an extended agenda, and for this 45 to 1 hour webinar, we can only barely scratch the surface, and we cannot really claim to go in any depth in any of the topics. Data science definitely is going to be very popular in the upcoming years, and it's a very extensive, broad, and deep topic. At least we will talk about some of the terminology, concepts, algorithms, some of the tools used by solution architects in various scenarios. We will try to define data science. We will also cover data analytics lifecycle. The assumption is that you are in some way doing the job of a solution architect. You might be an enterprise architect, you might be tech lead, the senior designer, senior software developer. We're not going into every algorithm in detail because it would take a great deal of time. And again, as I said, the classes which will be given to you at the end of this presentation will give you a little bit bigger scope for learning data science. So I would like to make this session as interactive as possible, so please don't hesitate to fire off a question. There is a questions pane that you can put in your question, and if I will be keeping my eye, don't use anything else like chat or emails or what's not. Use the questions pane. That will be the only place for me. I'll be running this show by myself, so I don't have any assistants to help me with taking the questions and arranging them. Okay, so data science algorithms, analytic methods. Again, terminology, the primary algorithms and techniques used in the area of supervised and unsupervised learning, and choosing the right processing system. That's probably the most critical. But I guess we will be covering a wide range, kind of a broad spectrum of those tools, desktops ranging to the tools in the Hadoop product ecosystem. So data science, essentially, it's a new discipline, and in one way or another, it has been known as data mining, business intelligence, and what's not. Essentially, data science tries to accumulate the wealth of expertise accumulated in every respective field, and try to help data scientists, those data practitioners, to extract business insights from raw data, right? And for that, you would be applying a wide range of theories and techniques and algorithms, from statistics, data warehousing, data visualization. So I guess one analogy that I would like to kind of draw is the webmaster, the role that used to be all the rage at the end of the last century, right? So this guy was responsible for sysadmin jobs, for writing CGI scripts, HTML, and what's not. So wearing all those hats was quite a formidable task, quite a tall order. But I guess, of course, that person, she or he, would only be able to be good at a particular kind of a thing, maybe writing Perl scripts or something like that. And nobody really claimed, even though the job requirements push that person to do all the job. So data scientist in many ways is similar to that webmaster role. A very nice slide, which I guess puts everything in just one place, centered around data science. So data science, I guess, derives different pieces from a number of disciplines and areas, such as math and statistics on the right, as well as domain expertise. It's critical because you need to know what you are analyzing, garbage in, garbage out, right? Data engineering, scientific method. So I guess data science really derives this notion of a science, this term from the scientific approach, scientific method, where you would treat data or your data extraction as a scientific experiment. So you would be setting up, tearing down, applying theories, training models, and if those things don't work, you just move on. Advanced computing, all about, I guess, massively parallel processing on a cluster of machines, Apache Spark, for example, Hive, visualization, and on the left-hand side, you've got this hacker mindset. I guess it just correlates to that scientific method where when you combine those, you essentially become a mad scientist, right? So I don't know how you can manage that. Definitely, it's just quite impossible. And usually what you have is a data science lab of some sort. And that data science lab attracts and has on staff people coming from different backgrounds, having different skill sets. Okay, so I guess the term doesn't really matter very much, and you can use data mining in place of data science, as well as business analytics. But one of the differentiating factor is that data mining between data science and data mining is that data mining actually happens within the kind of a sandboxed data warehouse environment where you've got data mart, data center, where you process in a very kind of orderly fashion processing data. Data science activists, they are more of kind of a lesser strict in this regard, and they have less restrictions, and that leads them towards using NoSQL open source products, not only relational type of database-based tools. They don't care about enterprise ready, maybe security and other stuff. Sometimes they use public cloud infrastructure for that matter. So data scientist is someone who, I guess, doing lots of things in a variety of fields. You would be familiar with statistics, machine learning. You need to have good programming skills. I guess one of those factors that you need to take into account is that you need to have good programming skills. Not in one language. Some people say, okay, if I learn Python and scikit-learn, would I be a data scientist? Probably not. You would probably be better off to pick up some R, maybe Apache Spark using Scala. And essentially, you might not be a very good programmer as such. So kind of knowing all the kind of nuts and bolts and very nitty-gritty details of every system. It would be more important to understand the data structures like pandas and maybe data frames in R. And all that coming together would give you probably a good cross-language view of your data, because essentially, again, a language, it's just a tool, right? And the more tools you have, and every tool is for a particular job. R and Python, for example, they compete head-to-head, but they have respectively advantages and disadvantages. You need to have hands-on experience with scalable computation, because appetite comes as you eat. If you have initial success with a small subset of your data, someone would come along asking for more, so that you would start working on big data. Big data in terms of not only size, but also the variety of data. So it can be unstructured, JSON, XML, what's not. Okay, you need to be able to communicate. That's a given because you will be mostly working with business-minded people. You need to understand their language, and you should have a very unobtrusive way to teach them that language. Okay, domain knowledge, the problem domain we are working. So again, as I said, Gigo is still applicable. Jeff Hammerbacher used to be a data scientist who built and led data scientist group at Facebook. So what he described as his group's activities on a given day, you would be doing any of those activities, right? So a hypothesis test, it's just a basic statistics thing, but at the same time, you would be going through data-intensive processing using Hadoop. And again, let me reiterate, communicate the results of the analysis. That communication is very important. You as probably understand, I don't want to preach to the converted, you are architects, and this is absolutely indispensable. So if you have problem to explain things in a very concise, high impact kind of a word, kind of 2 minutes while you were going up in the elevator with that very busy CEO level who is just rushing out early on Friday to play golf or things like that, you would probably be not able to communicate the excellent results of your work. Again, continuing with data scientist environment, you would be working with business. You would be also required to clean up and prime your data, to remove outliers, any noise. And when you're doing so, you need to make sure that those outliers, quote unquote, actually represent noise rather than a kind of aberration rather than valuable information. Right, removing non-actionable data, definitely it should happen during the data capture. Right, so don't try to collect as much information as you can. Sometimes it's counterproductive. It creates kind of a more of trouble. But with the current type of data lakes that we have based on Hadoop or otherwise, you pretty much are not restricted. So get as much data as you can. But early in that development cycle, you should go after all that unnecessary data and just probably get rid of it, or maybe compress it and put it somewhere far away. Maybe you would use Glacier cost-effective storage on Amazon, where you would pay a fraction of a penny for gigabytes per month. So opportunities are available, and you should explore those so that you become an efficient data scientist, right? And then creating very fine models is critical. So, but that's where actual data science begins. That's where that kind of very interesting, very, I would say, high priest type of work environment. You would be just performing some magic to extract data. Validating models with business, and then work with software engineers to make them actually implementable in some practical applications. Some of the examples, basically you can build a basic correlation model, request research for based on your product reviews. So you would be probably collecting information from the Twitter feedbacks and maybe monitoring Facebook or other social media, trying to understand users' sentiments, predict users' choices, and prepare appropriate recommendations to maybe modify certain parts of the product, some features. It's important to engage people, your clients, your business in a feedback loop, so that the shorter feedback loop, the more quickly you can adapt your product to new requirements and just account for any possible mistakes, omissions that you might have. Okay, and some others like customer segmentation model and traditional type of business analysis. Gotchas, the potential traps that you can find yourself into unknowingly is that you're dealing with lots of noise, and that noise would result probably in your models overfitting overfitting the data and not giving the actual good presentation. You would be overwhelmed with the influx of data. Gigo, sometimes people who have formal education in statistics, people holding PhDs and people from academia, very respected people in their community, and they really have great respect in what they're doing. They definitely are probably someone who has a wealth of knowledge about math, about statistics, about lots of things, but sometimes it might get in the way. Sometimes simpler models would be more appropriate and effective, and unfortunately those people like from academia, they don't like simple models, because sometimes complexity gives them that satisfaction, that beauty of the products that they create, right? And you cannot blame them for that. So there should be a kind of a good balance between a good deep model with lots of flexibility, lots of tunable parameters, but at the same time keeping it simple helps you to see a bigger picture, kind of removing that overfitting and speeding up processing, making your model next to real time, so that you can, I guess, add it to any data feed happening in your online presence and extract the data and I guess provide some recommendations in real time or near real time. Communication channels should be open. You need be aware that you are doing the right thing. Validation is very important, so run it by business if you are not really a business-minded person yourself, because business owns everything, right? It's not IT or data scientist who owns something, even though it's kind of a very kind of a cozy feeling, but in fact business does. So you can be, I guess, a little bit disillusioned by this fact, but that's the way of life. Okay, ouches, right? So when you work with business, it should be happening as early as possible in that development cycle. Business might tell you, yes, we know that already, so tell us something that we don't know, right? Very frustrating, right? And another response from business would be, that's not how we talk about our customers. There is something wrong. Try it out again, right? And the problem might be you would be arguing quite heatedly within your group as to what that K in the KNN should be and things like that. But in fact, the time that you spend on development, it might be months, weeks, months. You should probably again make that type of response less hurtful for you. Okay, so life cycle, the big data analytics pipeline. It doesn't matter what the size is. Big data is just a little bit of a misnomer, I guess. We like put a label on certain things that potentially might describe everything, but it ends up describing nothing. But people agree to that. People like, I guess, something that you can attach to, so that you've got big data, you've got NoSQL type of kind of discourse, and people don't really mean the same thing. So you start with data extraction, right? That's something that you should be aware. So your organization should have channels open for data ingestion, like data collection. It can be anything, feeds from social media. It can be data from your sensors, from your web log files like Apache log files and what's not. You need to clean data, perform a number of I guess exercises. At this point in time, it's not that critical that you actually make data compliant with a particular schema. So if you work in with a relational database, in the traditional data warehouse environment, you would probably be making sure that your data is properly cleaned and it complies with the DDL of a particular table, right? Otherwise, your import operation would fail, and you would need to manually update your data. At this point in time, you can start, I guess, if you do a very deep cleaning of your data, dimensional mapping, creating all up cubes, you can start producing reports just on the raw data, right? So nothing really prevents it. But then, I guess, more interesting stuff happens down the road. You start actually working on data, acting on the data as if it was your data experiment. You start doing data science experiments. So you need to perform data sampling, selecting some parts of your data, 3/4 of your data for training, and 1/4, 25% for testing, feature selection, ordering features, removing correlated features, modeling data. And at this point in time, you would develop a candidate model. So based on supervised and supervised learning and what your gut feeling, your background tells you, or the guy who is sitting next to you like tells you what it looks like would be the best way to process your data. You start training. You would get a sample of data, you would train your model, you would come up with an algorithm, then you would use a language of your choice, a platform of your choice to build the model, and then you would need to train the model. You would need to teach the machine or let the machine learn itself what the data is all about. And then when you do that, you need to validate your model. So you would feed the test data and see what is the error level, how fit your model is. And if you're satisfied, if not, of course, you would go into another cycle. You kind of discard the existing model, and you would go within. You would suggest a new model. Model validation, and again, when you come up with a model and have some kind of early results, at this point in time, it would be a good idea to touch base with business. Up to that point, probably it's not really worthwhile, but during the cycle on the right-hand side, it's just a repeated iterative process, and you would be constantly in touch. Just wake them up in the morning at 3 o'clock saying, you know, I've got very good results. Just let them feel that excitement that you have. Okay, model should be accepted. All the, I guess, parties involved should clear off, and just you'll be ready with a rollout. So all those life cycles that we've talked about are listed here. Data discovery, I guess at this point in time, you would probably create the data, I guess, capturing channel, maybe from scratch, or maybe you would just attach that data discovery, data harvesting kind of facility to get the data out of a particular source. Okay, production rollout. What else? Data discovery, I guess in one way or another, I have already talked about this. Data that you are extracting is driven by business, so what business is looking for. Like sentiments of people, or they would like maybe to get a deeper view of some relationship between particular products. You need to identify the potential size, because that would be a dichotomy for you to go with a desktop type of processing, or Hadoop, or any other massively parallel processing system such as Apache Spark standalone. Setting up the lab for processing number of computers, people, budget, lots of things. And it's important to have a very good rapport, very good understanding within the group, so that there is no contention, no religious wars, that someone is promoting Python over R, and people are just spend most of their time just arguing. Okay, data harvesting, we know about the ETL. We extract the data, and at this point in time, it's interesting that for NoSQL systems and Hadoop systems, the transformation is actually extracted and delayed, deferred until a later moment. So we just extract data and we load the data on the storage of some sort, and we perform transformation on demand, like data on schema, schema on demand, flexible schema, schemaless term, and any others. They just indicate that you can apply schema on demand. So schema needs to be applied, because without schema you don't know what you're doing. Data priming, cleansing data, removing any noise, potential outliers. Right. At this point in time, you potentially might want to augment your data enhance, so that you would replace certain anonymous tokens with specific data, or maybe combining, adding some additional data, like you've got potential, like several fields in your data set, and you would like to add an additional data column which you have acquired from another source, and did kind of a inner join and then added that thing, so that you would have kind of a more complete view of your data. Right, that data aggregation when it happens, it is much better. It potentially produces better result when your data is really properly enhanced. Right, so you can do counting, you can do finding the mean within a group. So grouping, that essentially what you're looking after, because that data partitioning, segmentation as per a specific group. It can be geography, it can be, gender, it can be income brackets and what's not. Okay, data normalization, it's not about relational normalization of data sets, because the opposite is true. Data science is all about denormalizing data. You have to unlearn many things in terms of like third normalized form. Forget about it. Just you can have everything all value deprecated, as long as it don't conflict with the master records, and you know how to actually manage that complexity. Right. Normalization is about bringing data to kind of a level of values where you can compare various features, variables together. Right. They sometimes can be vastly in scale. For example, if you're comparing, I don't know, the national product of various countries, right? So some countries have just an enormous, huge product, and others would not have so much. And I guess some normalization, if you just take into account that as a factor rather than an absolute value, and you're interested in producing some sort of a cumulative value or kind of a aggregated value, which takes into account life expectancy and what's not, then it would be, I guess, important for you to normalize data to a certain extent. Modeling planning, you should select the most appropriate machine learning or statistical learning. At this point in time, you need to have some sort of sampling of data. You don't need the whole terabytes or petabytes worth of data. Just selecting a subset of data and see how you can, I guess, get some preliminary results. And that would be the point in time to have a touch point, touch base with your business. Model building, you build the model using any of the available algorithms. Currently, it's just amazing the amount of efforts that people are putting in the language of their choice for any data science type of work. Python, R, just Scala. And those platforms are open, meaning of course, you probably wouldn't be, but if acting as a contributor to those packages, even though nothing prevents you from doing that. But I guess that the wealth of, algorithms available on tap for you, just mind-boggling. You need to take into account runtime performance, because if you've got a specific requirement, like non-functional requirements that your application should run within, I don't know, sub-second interval, so that it can be attached to a particular new real-time system, you should take into this account. Again, resources, CPU, what the machine should look like. All machine learning algorithms are, most of those are CPU intensive, and they are memory intensive. Of course, currently we are not limited by the amount of RAM that you can purchase. You can get a machine in the cloud. Amazon offers you currently extra large instance flavor of a virtual machine, which comes with, I guess, 100 of terabytes, not gigabytes, terabytes of data. Right, of course, it costs money to upload the data, load the data, processing just a couple of bucks per hour. You'll be probably paying for the storage. Okay, and but the problem would be that if you've got regular processing system like heap-based, whether it's Java or Python, garbage collection is important. R is not very good at managing large data sets because the garbage collection kind of policies and certain things would influence your choice of a system. Communicating results, I guess it speaks for itself. I guess sometimes visual, a picture is worth 1,000 words. Rollout, I guess when you roll it out, you should have a kind of a warranty period where you can babysit and fix any problems that you might have, right? At this point in time, you would probably be able to collect some additional information so that you can, I guess, further train your data so that you can enhance your model and make it more fine-tuned for the tasks that you currently have at hand. Okay, algorithms and data analytics methods. A whole bunch of those are listed here. KNN, decision trees. I'm not going to read all those. If they're familiar to you, so be it. If not, then I guess just take my word for it that it's just a very small percentage of those available. A critical factor for you to take into account when you decide which type of algorithm to choose. Essentially, you've got two types of machine learning, supervised and unsupervised. In supervised learning, you've got, you need to train the machine. You need to feed the trained data set so that they would be actually able to predict data. In unsupervised learning, you pretty much let the machine learn from your data, and that's the real machine learning. Right, so for supervised machine learning, out of those two slides before, we can select naive regression based KNN. Again, and regression can be has a number of derivatives, linear, simple, and what's not. Unsupervised machine learning, K-means, a very popular one, clustering, and what's not. Choosing the right processing systems. I guess that's where you would probably step in and start really thinking about how to actually help your organization. R is a desktop open system distributed under the GNU public license, so you cannot combine it with any other proprietary tools because of that license. Know about this. R is extremely popular with people working in statistics and machine learning. And I guess in many cases you can, I guess, replace Excel, SPSS, SAS, and what's not proprietary, paid-for, licensed type of systems with R. Out of the whole list, I would suggest using RStudio as the last bullet. Right, there is RStudio Desktop and RStudio Server, where you would be able to communicate your results across, I guess, geographies. So you can have people working offshore onshore, so that the work done by people living in the earlier time zone can start the work, and you would kind of a process, so that the output of your work would be later on used by your colleagues. R implements a wide variety of statistical algorithms. That's how it was created, but in addition to the statistics, it also supports machine learning, such as classification and clustering. Right? There is a very vibrant community, and there are about 10,000 packages currently available, with varying degree of, I guess, robustness and kind of a user friendliness. But you can always get documentation. You can always, I guess, ask a question on the forums. Data import, critical for you to know that data import is critical for R. And you can get data out of JSON documents from various systems, SAS, SPSS, Excel. And it's as easy as kind of a loading library of that name. You can download, the repository contains all those things. Essentially, most of those are ODBC, Open Database Connectivity Driver based, I guess very efficient. Data export, so when you process your data, you can export data, dump the data, and further import it in all of those systems, right? So that's kind of integration points. It's kind of a bidirectional. That would be probably a good place for you to start working with R. You take the R and try to kind of unobtrusively incorporate it into your into your workflow. You will still have Excel and whatever license you have for whatever system. But at this point in time, you will see how R can match up, how you can easily integrate. And at a certain point in time, you just cut off any of those systems that you find essentially that they not a match to R. And definitely R, in most cases that I've seen, can be, I guess, regarded as a more cost-effective solution for the tasks that you usually deal with. Apache Hive is a Hadoop based product originally developed at Facebook. It gives you SQL type of language to process data on a cluster of machines. Right? So essentially you have that illusion that you are working against a relational database, but in fact it's not. Your data might be unstructured. It's just a matter of defining your data in a way using a DDL script to present it as if it's just a relational database. Okay, if something is not probably fitting in very well because of that schema on demand, then the data would be just ignored or represented by null. Your transaction wouldn't be kind of a rollback if you just execute a select statement or any other type of operation supported. Okay, so of course we just barely touched the surface. I don't see any questions coming in. Definitely, it's just a very kind of a high-level overview, and in order to really get yourself more engaged on that front, you should, I guess, look at those courses. There are 4 days, because at the end of that 4th day, you would be absolutely exhausted. The 5th day, we dropped that, even though I guess we have material enough to cover that, but 4 days is absolutely the maximum that people can tolerate. Okay, so we've got data science for solution architects, and we've got data science and big data analytics. They've got some overlapping content. They are not absolutely, I guess, segregated, but they've got some distinguishing. So visit our website, Web Edge Solutions, and look up the outline. So there is an outline which spells actually every bullet on a slide, and it lists the labs that you are going to do. Labs are indispensable. That's what I guess makes us different from other companies that we we have a bigger focus on doing hands-on type of exercises, doing labs. Okay, so questions. The question is, in the data analysis pipeline, where will the solution architect be requested, will be required the most? Okay, let me go up. I would say probably in the first part. When it comes to, hopefully you can see my my cursor, during data integration, cleaning data, and potentially data sampling. So I would say solution architect would be playing a very important role here. Essentially, you need to provide your expertise for data discovery, data harvesting, and potentially data priming, those three activities.